Welcome! In the previous video, we drew ASK, FSK, and PSK at a millisecond timescale with a 1 kHz carrier. Today, we do exactly the same thing, but 1000 times faster. The time axis is now in microseconds, the carriers are in megahertz, and the data rate jumps from 1 kilobit per second to 1 megabit per second. Here is our digital signal x of t, 8 bits in 8 microseconds. The pattern is 11110001. 4 ones, then 3 zeros, then 1 final one. Our job? Draw ASK, FSK, and PSK for this signal. Before we start drawing, let us figure out how many cycles fit in one bit. The carrier is written as sine of 6 times 10 to the 6 pi t. To find the frequency, compare this with the standard form, sine of 2 pi f t. Setting 2 pi f equal to 6 times 10 to the 6 pi, we divide both sides by 2 pi and get f equals 3 times 10 to the 6, which is 3 megahertz. Now, 1 bit lasts 1 microsecond, which is 10 to the minus 6 seconds. The number of cycles in 1 bit is frequency times bit duration. 3 times 10 to the 6 multiplied by 10 to the minus 6 equals exactly 3. So we draw 3 complete sine waves in every 1 bit slot. For the FSK 0 carrier, sine of 4 times 10 to the 6 pi t, the same calculation gives f equals 2 megahertz, which means 2 cycles per bit. Let us start with ASK. The carrier is sine of 6 times 10 to the 6 pi t. That is 3 megahertz, which means 3 full cycles per microsecond. ASK rule. Carrier on for a 1, off for a 0. Bits 1 through 4 are all 1s, so we draw 12 cycles of sine back to back, 3 per microsecond, 4 microseconds. Bits 5, 6, 7 are zeros. The signal drops to 0 for 3 microseconds, no oscillation at all. Bit 8 is a 1, so we draw 3 more cycles of sine in the last microsecond. Compare this to our previous video. There we had 1 cycle per bit at 1 kHz. Here we have 3 cycles per bit at 3 MHz. The waveform looks much denser, but the principle is identical. Now FSK. The rule is, a 1 is sent as sine of 6 times 10 to the 6 pi t, 3 MHz, and a 0 is sent as sine of 4 times 10 to the 6 pi t, 2 MHz. 3 cycles per microsecond for a 1, 2 cycles per microsecond for a 0. Walk along x of t. Bits 1 through 4 are 1s, 12 cycles of the fast tone over 4 microseconds. Bits 5, 6, 7 are zeros, 6 cycles of the slow tone over 3 microseconds. Bit 8 is a 1, 3 cycles of the fast tone in the last microsecond. Notice, the carrier never stops. During the 0 bits, you still see oscillation, just at a lower frequency. The transition points at 4 microseconds and 7 microseconds show a visible change in oscillation density. That density change is the information. Finally, PSK. A 1 is sent as sine of 6 times 10 to the 6 pi t, and a 0 is sent as cosine of 6 times 10 to the 6 pi t. Both are 3 megahertz. The frequency never changes, only the phase does. Cosine is sine shifted by 90 degrees. Bits 1 through 4 are 1s. 12 cycles of sine over 4 microseconds. At 4 microseconds, the bit flips to 0. The waveform switches to cosine. Same frequency, but the wave now starts at its peak instead of at 0. That is the phase jump. Bits 5, 6, 7 are zeros. 9 cycles of cosine over 3 microseconds. At 7 microseconds, the bit flips back to 1. Another phase jump, back to sine, 3 final cycles. Only 2 transitions in this pattern, at 4 and 7 microseconds. Each one shows an abrupt break in the waveform. Let us summarize and compare the two scales. In the previous video, 1 kHz, 1 cycle per bit, 1 kilobit per second. Today, 3 MHz, 3 cycles per bit, 1 megabit per second. 1000 times faster, but the exact same 3 modulation rules. ASK, amplitude on or off. FSK, fast frequency or slow frequency. PSK, sine phase or cosine phase. At 1 megabit per second, this signal can comfortably carry a digital voice channel, which only needs 64 kilobits per second. But it cannot carry a digital video channel, which needs roughly 96 megabits per second. That is the practical context. The modulation scheme you choose does not change the data rate. It changes how robust, how bandwidth efficient, and how complex your receiver needs to be.